Thank you very much, Lake. This has been so great. I got to say, I'm right in the middle of it. And to hear John Callies and Lake and just all this great information being shared, I want to encourage everybody out there, if you're watching along, just keep listening. And if you have questions, throw them up in the comments section. I've been noticing that people are just interacting. It's become social in there. We really appreciate it. And remember, we're going again tomorrow. We're going to do it all over once again. Great stuff, and I appreciate it. And as a fan, to hear some of the stories of NHRA Pro Stock that I was in the grandstands watching, Butch Leal at the Gator Nationals in the 1980s, and hear the stories behind the scenes, priceless stuff. But now we are back with Chuck Lynch. Chuck was on yesterday, and Chuck, today we're going to evolve the program a little bit, delving into valves and valve seats, a whole lot of information. You guys at the AERA providing information for a lot of folks out there. First of all, how you doing today?
I'm doing great, and yourself?
Oh, my goodness. I couldn't be better. I'm like surrounded by legends of performance in motorsport right now, and we're going to keep it moving. Yesterday had a lot of interesting information about surfaces for gasket surfaces. I'm taking a lot of that home with me. Today, what are we going to be focusing on? I know valve seats. Heard a whole lot about valve angles and how important and significant that is. So where are we going to dive in this segment?
Yeah, actually, I'm going to cover some of the materials that are available out for use, and also to follow up on the seat and guide machining component of it. The importance of the guide. Oftentimes we focus a lot on the seat, but just how important the guide is. And there was some mention of powdered metal guide, so I want to speak on some different guide materials.
Let's dive in there. And first of all, I appreciate you obviously have a studio going on over there. This is not your first rodeo at the Engine Performance Expo. You're obviously used to doing these kind of things, and you're all set up for it. So let's dive in.
All right, thanks a lot. So in a little earlier conversation, I'm going to try to do this, just from my bullet points and share the information. If we get something that I need to bring up a diagram or something of that nature, then I'll share my screen here. But so starting at kind of the top, and from the top of the head. So the valve guide, again, it's so underappreciated. I take these calls on the tech line all the time, and I've worked with Ed for a lot of years. I actually used to work for Rottler back in the day when Ed was still at Sun, and he and I worked on the transitioning from vitrified abrasives to diamond. So I started working on that in 1995, actually. But anyway, I digress. So the valve guide, you cannot produce accurate valve seats if you do not have an accurate guide. So I challenge everyone to really think about how important sizing, surface finish, cylindricity of your valve guide is. And then as you move into the seat, how much better a seat you can make when you have a good reference point. Some of the challenges that we have today, and it was mentioned about that Coyote, is the various different powdered metal products. Now, there's tons of cast iron guides still available, bronze guides and stuff, but by and large, they always have all moved to powder metal products. That said, the PM products can vary in hardness, in the composition. During my tenure over at Clevite, they actually had 24 different valve guide materials in powdered metal. So adding hard particles, cobalt, tungsten, these things that we talk about with powdered metal seats, well, they exist in these powdered metal guides as well. Some of the powdered metal guides, in the manufacturing process, and this is true of a valve seat as well, they actually use like paraffin or a wax to get that to stay in that form when they press it into a shape. Well, they can take opportunities like that to put in lubricants that will be activated by heat. So when you start that engine up, the guide can actually weep a lubrication, and then when it cools back down, it acts like a sponge, and it will pull lubrication back into the guide so that you have startup lubrication. But again, you're still surrounded by very hard particles. So when you do have film breakdown, then those hard particles can wear out valve stems, or that high friction area can actually, you'll see guide wear. But the powdered metal guides are pretty tough for us in the aftermarket to machine too. They need some unique strategies and approaches. You need a good depth of cut to create the chip, where oftentimes in the cast iron, the bronze, and so forth, you typically would machine the guide to the next oversize with a very little chip load. So you would have a guide that's, say, a number everybody's familiar with, like 11/32 guide. If you're shooting for 343, you may have a guide that's 342 and you're only taking out a thou or so. A lot of the PM stuff, they're going to have you to try to create a pretty good sized chip. So you may be going and working on a guide that's, say, 40 thousandths undersize or a millimeter undersize. So that can give some real challenges to trying to machine that. That said, a lot of people opt to replace a PM guide with cast iron or bronze or a liner or something of that nature. Guide tolerances. Guide ID and taper should not exceed a half thou from end to end. Again, that's our datum point for the guide, or for the valve. So we really want to control the valve as it travels away from and back to the seat. So spend great efforts at making sure that you have good cylindricity, keep taper to a minimum, and it'll serve you well in trying to machine, because again, when you're at the machine and you try to reference from that point, the further you are away from the guide, that's, it's kind of like using a crane. The further away from the lift point, you're going to have more articulation. So if you have a lot of taper in the guide, it acts like a funnel trying to control the valve back to the seat. Likewise, that's going to have the same effect when you're trying to reference that as a point to cut your valve seat. So some seat issues that are often caused by the guide: random valve seat runouts. Now, we've watched valve seat concentricity being measured multiple times today in some presentations, and that is super important. So again, if you don't keep guides under control, then that's one of the things that you can chase is random seat runout. You can have issues because you're not rigid in your setup. You can have chatter, and you can have differing results when you go back and try to cut that. So, okay, I don't like the number that I read with my concentricity gauge. I go back and measure it again. It's totally different. The high point was at 2 o'clock the first time, and now I measure a high point at 6 o'clock. So what's going on? Poor or varying vacuum test results. One thing that I want to share, and we talk about concentricity, and oftentimes we'll refer it to the valve head diameter. There's a rule that's been around for many, many years, and it's usually a thousandths per inch of head diameter we kind of consider acceptable. But because of the materials, we keep tightening up our stem to guide clearances. So if we can run closer stem to guide clearances, then that valve does a better job of hitting the same place on the seat. Well, that said, say if I've got a seat that's got 2 thousandths run out, and I have a valve that's got a half a thousandths run out, but I'm trying to run 8/10 stem to guide clearance, think about the coaxiality issue that you have between those parts. You will be rubbing the valve stem against the guide. So you really take that into consideration. Hey, I should have seat runouts that do not exceed my stem to guide clearance. So again, as we've tightened those up, we've not really changed that rule on how much I can allow for valve seat runout or valve head, or the valve head runout of the valve itself. And then we tighten those stem to guide clearances up. there will be contact. So again, think about that. If I'm going to run a thou on my sim to guide clearance, make sure your seat run out and your valve run out is not beyond a thou. Pilot selection should be an indication of guide quality too. So again, we're talking about machining, valves and valve guides, the seats, as much as we are about what valve materials are out there and available. If you keep your guide sizes very, very accurate and you only need to use one pilot to do that whole head, that's ideal. So if you're going along and you do like a fit check with your pilot, and it should be really a good telltale sign of, hey, this thing seems equally difficult to install in each guide. For the Rottler stuff with the dead pilot, there's just a taper. It's about 3/8 of an inch from where it transitions from the pilot end to the larger end where the tool works around. In that transition point, there's actually a gauge that shows how far it's inserted into the guide. So those should be good telltale signs of how consistent your machining of your valve guides are as well. So again, we want to stick to one pilot size, and we want to make sure that it installs the same height across the head. So the valve seat, we'll start with a basic first. So what's the purpose of the valve seat? It's to provide combustion seal. It's like those 55-degree seats that we're talking about. Over the years, you take a look at, say, a Briggs & Stratton or a flathead engine. They had real flat angles. That's because they were looking for some greater cross-sectional area to improve airflow across that. If you take a 45-degree seat and you look at the area between the seat at max lift and the valve face, as opposed to you got a 20-degree seat. But the negative side of that is wedge pressure. It takes much more energy to seal that combustion when you have those real flat angles. The diesel world's done that in the past when more of them were naturally aspirated, an opportunity to try to fill the cylinder, and then they have all that cylinder pressure, and then they fight combustion seal. So those steeper angles, like that 55-degree seat, I know we look at flow, but a 55-degree seat, that's a lot of wedge pressure. You can run a pretty narrow seat width and still make that thing seal. You can kind of liken that to a Morse taper in a spindle of a machine. It's absolutely amazing that with a Morse taper tool, you can stick it in a machine and that tool won't fall out. And it's just wedge pressure. So, you take a look at valve seat contact and how important that wedge pressure can be. Negative side, when things get a little bit out of whack, they quickly destroy themselves. Valve seats beat in, valve faces eroding. So that's where you want to have good concentricity. That's going to help you control your heat transfer from the valve head into the casting. And again, we also use those to tune airflow dynamics. If we're looking at tumble, turbulence, that's done a lot with the valve seat. When it gets into swirl and things of that nature, then port designs and so forth can really have a big impact. In the diesel world, you have the re-entry bowl, entering bowl, and the pistons. They can actually hugely impact the swirl characteristics as well as the tumble characteristics. So again, I'll just hit on again as we're talking about the seats, that thousandths per inch of seat diameter, really consider your valve guide clearance. As you reduce that clearance, remember to take the run out allowances with it. When machining valve seats and cast iron heads, lubrication is not really necessary, but on like aluminum heads, you may pick up some material around especially if you're using radiuses on a big form tool or whatnot. And so you might use some lubrications. Something that I've really liked in machining valve seats is just simply kind of spritz it with a window washer. It does a terrific job. Kind of washes away, it evaporates, but it keeps that aluminum from sticking to the insert tooling, and can really improve surface finishes.
Chuck, are you still with us?
Yes,
Okay.
yes. Sorry about that.
No worries. And while we took a quick pause there, I just want to remind everybody that we will have a question and answer session at the conclusion of this. So as you go through, if Chuck has covered anything and you do have more, are looking for a more in-depth answer, you will get the opportunity. So just be ready in the comments section at the conclusion. We're going to go through a Q&A with Chuck. Chuck, resume.
All right. So, as we look at materials that are used in seat and guide machining, most of it's carbide. I've seen in the comments in the chat box earlier, someone making a comment about the surface finish speeds on cutting valve seats. And, some of the machines, you'll see they'll easily run 1,000 RPM spindle speed, but we're typically using a carbide, so a tool that doesn't need that kind of surface footage. So, just taking a quick example of 1.25" seat, you should really run that thing somewhere between 150 to 450 RPMs max. The smaller the seat diameter, of course, the higher the spindle speed you can run, because it's all about surface footage. But that's one of the things that I see. I actually travel to shops as well, is people tend to think that they should run much higher spindle speeds, and that's very hard on the carbide. I've seen where they chip in the apex in the transition from, say your top angle to your valve seat angle to the throat angle, simply because there's so much heat induced into that because they're overspeeding the carbide. So there are charts that are shared in seat and guide reference books, and or you can reach out to us at the AERA tech line, and I'm more than happy to share some of that data and information. We're always trying to, help everyone out as much as we can, whether it's technical data or pointing them to it's someone in the field that can help out. But that is something you definitely want to consider as a factor when you're machining. It saves on tooling, and it can also keep you from cutting the seats in too deep, too fast, material pull out, and so forth. Some things that impact the performance of your seat and guide work could be sharpening. What happens is, most especially when we're using form tools, is people tend to get a little bit rambunctious and carried away, and they'll put taper in the face of the insert so that it's actually, you got a profile that may look more like a chopping axe than that nice square edge that the machine, or that the insert was actually initially machined to produce. So keep that in mind. Poor sharpening practices can cause you to have to sharpen much more. So you don't like the result of your seat. You see striations in it because you got chips and things of that nature. So really, have maybe a jeweler's loop, a magnifying glass or something, and look at the results of your sharpening, because that can save you on a lot of rework. Use the most rigid tooling available. It's available to you for a particular application. Deflection usually leads to batter, which leads to poor heat transfer, and again, rework. For the guys using the form tools, as the actual insert holder, those things have a range of diameter that they're designed to work with. Don't push those beyond the seat diameter extent that they're used for. Then that's where you start to get deflection. So think about that. Am I okay using this 2001 when I should be at a 2002? Give that some consideration. Don't push your tools beyond their extent. Some other challenges is like high nickel seed alloys that may be kind of stringy. Like we were talking about in the resurfacing yesterday, if materials bond themselves to the insert tooling, what does that leave to the surface? So you may have to go and lap seats or grind or something of that nature to remove some of that material that bonds itself to the cutter. Oftentimes that's also induced by the approach at spindle speed when you're machining that. So again, and maybe some of the lubrication that you might put on the seat. When it comes to form tools, where you might fight valve seat runout issues could be wear in the tool bodies, wear in the ID where the pilot fits up into the tool body, or wear in the taper where it goes up into the spindle. I think it's underappreciated in how well you should maintain that long taper that goes inside of the spindle. Tools get knocked around, bumped into each other, and you think about it, for every action there's a reaction. If I ding that body, there's going to be material that's pushed out by the little dent that's going in. So that may actually cause that tool to not locate properly in the inner spindle, and now I have an eccentric effect going on, and then I'm trying to get valve seat run out that's, again, less than 1 thou per inch of seat diameter. And then I'm starting with 3 thousandths eccentricity in my tooling setup. Insert pocket holders can lose angle after time. We don't realize it because we've got so much mechanical advantage with that steering wheel, or even if it's a CNC automated machine where it can kind of pack and apply that load, that it actually, if you've got a lot of throat angle, you can rock that insert and start to break up that V. So again, use heavy duty insert holders and make sure you keep eye on your contact angles, that you aren't losing those. One of the things that you can have with if you're using live pilots in your machines is if they hang up in the guide and not properly getting that material removed. So if they spin out in a guide and then they micro weld, and then, okay, now that pilot doesn't fit into my guide anymore, so I take it to the crankshaft polisher and take that material off. Now, did I lose location ability with my, my pilot? If it spins in the body, am I making the ID of that body bigger? And then one of the things about the live pilot is there's a set screw that's always going to push the pilot to the opposite side of the set screw. Well, you have to have clearance to have that pilot in there in the first place. So you're always working with an eccentric. I basically have like a fuel pump load. It's going to be running off center line. So the more my tooling is worn out, the bigger that issue becomes. And then we say, okay, always locate your head as rigid as possible. Well, in this situation, you would want the head to actually be able to move whatever that eccentricity amount is. Well, that's not practical. We all know that. So again, maintaining the tooling is as important as the specification that you're trying to yield. So we always talk about the big things like the machine, but sometimes it's the little things that tear you up, not the big things. Let's see, valve to seat contact. Why do we have interference angle? Now, this is always an argument. Now, guys in the performance world, I know that's a lot of our audience today. They do take the time to verify if they want 0 interference angle, and they match it. But you take a look in a practical sense. Okay, the valve manufacturer, he's got a degree angle plus or minus 15 minutes or a quarter of a degree is typical standard across the board. The insert manufacturer has his cutter angles are with a tolerance of plus or minus 15 minutes or a quarter of a degree. So which way are those going to stack up on you? So by and large, it's good to have that interference angle, and it does increase wedge pressure. Now, one thing, there's another theory with this too, based on the valve head construction. You have that deflection, your cylinder pressure trying to push the valve through anyway. And if anybody's looked at any Cobra heads that you pull the valves out of, and you know that you can shave with that valve, and even some of the LS engines with these extremely hard powdered metal seat materials that have particles such as tungsten and cobalt eating that valve head. So, you know that valve is trying to be shoved through the seat. So the theory is that if you have an interference angle, it usually under operational forces is no longer an interference angle because the valve is being pressed against the seat. So it's hard to say how accurate that is without doing a lot of, deflection measurement and so forth. But hey, that's not stuff most of us can do in our shop, right? That's more at the OE level. So in moving forward on like the materials, one of the things that we're really seeing today, and again, I mentioned the Coyote, some of the LS stuff, the 6.7 Ford's a good example of the 6.7 diesel is a good example of where what we used to call out as materials for intake exhaust valves is changing. The materials that were once reserved for high performance only have reached the level of everyday usage. In 2011 and 12, the Coyote engines had terrible intake valve recession issues because they used like an 8645 steel, and they've moved to 21.4N. Well, we used to use 21.4N all the time in the performance world, so it's very common. But again, you're seeing that trickle into the automotive sector. You're seeing Inconel facing materials applied to the stainless steels in the diesel world on the intake valve side as well. Inconel is a super alloy, high nickel material. Nimonic is a comparable to that. Again, those used to be reserved for your alternate fuels, dry fuel applications. Again, now it's common to see those in the exhaust valves of about every diesel that's hitting the street, and many of the turbocharged gas direct injected applications are now using Inconel exhaust valves. Stellite facing is one of those areas where we use that. It's a trademark name, and we say, oh, so it's Stellite. Well, just to let everyone know, there's actually at minimum 7 different Stellites that are used at any given time. Some of the stuff is, you have a Stellite 1, you have Stellite F, you have Ignite 6. So there's just tons of these different materials out there. So sometimes it's not just as simple as, hey, it's Inconel Stellite. So again, these are all things that are making us approach our machining practices differently. You need rigidity, and you need machines that can produce high quality speed with very little run out. Had someone share a video with me earlier this week in a project they were working on, trying to make some tooling to retrofit an old machine forward. And, I'm like, I'm sorry, but how far do you want to go? If you're only going to work on big valve stems like 11 32nds, 343, then yeah, you might be able to make that work. But as we work on passenger vehicles that have 5.5 millimeter stems, you really need to consider whether you want to do that. It doesn't take too many comebacks to make you wish that you had went ahead and purchased a machine that can do the work you want it to do. So again, it can be an expensive proposition, but as Cass was saying earlier, you can do learning by not having the guys who can meet your expectations. Sometimes can answer that for you. Okay, I have to have the piece of equipment that's going to get me that can achieve that thousandths per inch of seat diameter, that can help me generate this particular port design, because that's what the customer is asking for. I say this often. It's that quality is the perception of the customer. There's no real standard that says that's quality or this. You have to make the guy happy, and we do have standards. And like Randy said yesterday, what's the difference between a C clamp and a micrometer? That standard. So we have standards that we have to uphold and live to, and expectations of customers too. So we've talked about that in our podcast, AERA, the Engine Professional Podcast. Of sometimes if just laying out your expectations will also dictate what kind of customer you end up with as well. If a guy comes in and wants you to fix a one valve seat, he's probably not the customer you want. He wants you to fix one guide, one seat, things of that nature. So, utilize that in your decision making, and have the best equipment available to produce the best seat, the best bore, the best surface that you possibly can. And one of the big things that we struggle with is testing your work. And I know I've heard Lake say this a lot. If you don't have numbers or data, you don't really know where you're at. And so test your work. Concentricity checks, profilometers. You need that source of data to see where you're at. And like concentricity checks are a good way to test the condition of your machine, because if you're measuring valve seat runout, and I measure 6 seats, I got an inline 6-cylinder head or something of that nature, and I check 6 intake seats, and I always have a high spot at 2 o'clock. Well, I can make an adjustment for it because, it's always in the same place. So that's probably something machine induced. If I check seat 1 through 6 and I have a high point at 2 o'clock, and then I've got a high point at 5, and then I got a high point at 9 o'clock, well, that's probably either my process is out of control, as I say, the guide sizing. So it's all over the place. I'm trying to use the same pilot, and I just don't have repeatable location. So I need to address that. And sometimes it's just you got a gorilla on the machine, and they're really, really inconsistent. They need more training, and to work on finesse. So test your work. Vacuum testing. This is the big thing that I get on the tech line all the time is people don't have concentricity gauges because they can vacuum test. And this actually goes back to one of our tech and skills regionals. I made this comment, and before I even left there, we got some feedback from. So I said, a 25 inches of mercury draw on something. So your vacuum, most of our vacuum pump that we have on our seat and guide machines, or to check our work, they'll pull 25 inches of vacuum. That will collapse a 55-gallon steel drum. So a guy tried to do this. He actually took a steel drum, and it was the one that had the band around the top, so it wasn't fully welded steel.
And Chuck has frozen up just for a quick second. I do believe it will come back, but in case it doesn't, I would start getting your questions in the question and answer section, and we are going to dive into Q&A just moments from now. I know that we have gone through a lot of different material about tooling, about valve seats, about certain metal, etc., whether it's on the OE side or otherwise. But bottom line, we got most of the way through the presentation. Lake is going to jump in. Lake, I know you and Chuck work together on a pretty regular basis. As we said, this is the internet. We're doing great in terms of avoiding technical issues. He'll be back in a second, but the thing that he is running down, these are vital bits of information.
Oh, yes. I mean, Chuck is a wealth of knowledge. And the great thing about AERA is that they have won all these great webinars they've done in the past, lots of great articles, and it's pretty much, a lot of that material is free. If you go to aera.org, they have lots of papers that Chuck has written. There's digital copies of the magazine. So, I mean, Chuck is the expert on those things. So, oh, it looks like he's back. That's great. But yeah, I mean, for more on what Chuck's talking about, I would definitely recommend going to aera.org. That's the place where they've got tons of resources available. And are you back,
when
Chuck?
Chuck is back, Chuck, let us know when you can hear us and we can hear you.
I can hear you.
Excellent. But
All right,
since we're plugging stuff about AERA, they've got a podcast. There's podcasts available, and there's just so many different places to get knowledge. Like right now, a perfect example, Chuck mentioned that he has got a podcast. He is a guest on many podcasts, and that's just another way to kind of keep the information coming at all times. Chuck, back to what you were saying. We left you off just a few seconds ago. We got about 4 more minutes, and then we're going to dive into Q&A.
Okay, so I was talking about vacuum testing a barrel.
Yes, right at the exciting moment where we had an example with the barrel. What happens?
All right, so yeah, with the barrel, collapse the barrel, the lid blows off. So again, I was just saying that's just to lead into the amount of energy that's there available and how it can deflect a valve head. So I wouldn't trust vacuum testing to be my end-all be-all test. You still want to do concentricity to see what your equipment can produce, and you want to do vacuum tests because it will pick up things like nicks in valves, chatter, dirt, chips, because if you have a nick on a valve, that whole valve head is being held up because of damage. When it comes to chatter, that's usually high frequency. Well, the valve is just contacting very little area, so you will pick up that type of stuff with vacuum testing. But again, if you have a nice uniform seat that's 7/1000ths of run out, then you'll flex the head against the seat, and that's not good. That will, if you're lucky, it doesn't break the valve head off and it just wipes the guide out or starts to beat the seat out. But if you have too much flexing, then you have catastrophic failure type stuff. So again, measure your work. What gets measured gets done. And so use your measurements as a guideline for your maintenance. Again, simple things, as I mentioned, like resurfacing, but your equipment being level, the feet are truly grounded and on the floor. That's all very important. And again, that's one of the things that used to really drive me nuts on valve guide work, is that I would have all of these random run out issues and really push hard to make sure that we address guide sizing and guide cylindricity and what impact that's going to have on your ability to make good valve seats. When we talk about valve seat wear factors, again, as I had mentioned earlier, like with the Coyote, we more than ever, we really need to look at the compatibility between the valve and the seat material. The friction between the valve and the seat increases when combustion pressure increases, when thermal distortion increases, when seating velocities increase. Friction between the valve and seat decreases with lubrication and protective oxide coatings like You see more and more valves now that are black, that are nitrided. There's many, many types of nitriding, but that actually is a very good way within the valve processing without a lot of cost that makes a much, much better wearing valve. Used to, you've seen a lot of the nitrided valves are just nitrided on the stem, but now you're starting to see the tip, the valve face, all of those surfaces are nitrided to reduce wear, reduces friction, and actually a difference between nitriding and chrome plating is chrome plating is a plating. You don't do anything to the base material that improves the base material. You're putting a coating over it. So if anything happens, you wipe out that coating. But with nitriding, you're actually strengthening the steel alloy that you're working with. Now, some alloys don't take nitriding as well as others, but some alloys also don't like chrome as well as others. So if you have opportunities, that's definitely something to consider is nitriding. Now, some of the really high-end valves actually have moly coating on the stems. You have to be very careful about the transition area where you start and stop that. But again, it's so expensive that you're going to definitely have a very high-end application before you can utilize that.
So, Chuck, we've got some questions starting to queue up, and the one common thread that's running through the comment section right now in the chat section is they're loving the information, frankly. And so before we get to the questions, we referenced your podcast while we were getting you back online. Tell people where they can get a hold of you and get access to this information on a regular basis, because I know this is the kind of thing people are going to go back and play these videos. Our questions are populating, but give that vital information where folks can get a hold of you.
All right, so the lump sum of all of the places that you can get the information would be to first go to www.aera.org. .org is very important. There's some other AERAs out there. Get you to our homepage, and then we have a tech tab. And then that's where you can learn a lot about AERA's history. We've been around since 1922, so we're coming up on a 100-year anniversary. We've got members globally. I'm sure quite a few of the folks are online today. We have, software with engine specifications. Again, we have a YouTube channel, and recently we did start doing the Engine Professional podcast.
Excellent.
And we like to focus on, topics, particular subject. The most recent we've got out there is measure twice and cut once. So we're constantly looking for some feedback on some topics to discuss and looking to grow that.
Excellent. Well, we do have a couple of questions for you. We also have a limited time, so anybody that doesn't get your question answered, you can obviously go directly to the podcast and check it out. But here's one from Angelina. When is an interference angle recommended?
So interference angle is typically always going to be recommended. Some of the performance guys will know what works for them for a particular application. They may say, hey, I'm running mine 0 interference. But again, as I mentioned earlier in the presentation, the stack up of tolerances. So if you're not grinding all of your valves to match your seats, then you're probably going to have issue making sure that happens. In any service manual you look in, you're always, even yet today, you're still finding a full degree of interference angle.
Excellent. You referenced use some window cleaner earlier, and people wanted more information.
Yeah, so just so the stuff you would put in your car has got a little bit of methanol in it. It evaporates quickly.
Like Windex, like aerosol,
Yeah.
like they want to, they don't want to use the wrong thing by mistake.
Just the spritzer stuff.
Okay.
Something you put in a quart bottle and spritz it on. But yeah, window cleaner like you would use in your car instead of like Windex. So the gallon jug you would put in your sprayer container in your car.
All right, one more. What about using a light hand lapping for checking a valve job?
Surface finish does improve. You know, if you look at when it comes to machining, okay, boring, turning, milling, those are one level. Then you go to honing, that's precise. And then you go to lapping, which is the most exact, precise processes, you know, when you're measuring stuff light band or whatever. So surface finish, yes. Typically there's too much deflection to say, okay, I'm going to lap to fix a seat. You should only lap to improve surface finish.
Excellent. Chuck, thank you so much. Fantastic wealth of information. Everybody out there is fired up, and I guarantee you got more listeners to your podcast coming up soon. Thank you for the information and the presentation. Just great, and that's exactly why we're doing this here at the Engine Performance Expo. I know you and I have spent the past couple of days together, and you know, my brain is swollen with new information, so thank you for what you've done.
Thank you.
Excellent. Chuck Lynch with us. Now we're going to continue through the engine and kind of bring up a new subject. What a day, what a day, what a day. Yeah, my brain is swollen. I've learned so much today. They told us, don't start cars. We are not going to listen.